This is video 10 in the series of calculating the reinforcement of concrete slabs. This video deals with the method of equal deflection. Consider an isolated slab, simply supported on all sides, and take for instance the section YY, then you have this. Then there is a load transfer in the direction of Y, which is QB. And if you take a section according to X, then there is a load transfer in the direction of X, which is QA. The total load, of course, must be the sum of both loads. Take the section from YY, then this section with a uniform distributed load will have a maximum sag or a maximum deflection in the middle of WB. The same with the deflection in X direction, it has a deflection of WA. For compatibility reasons, WA must be equal than WB. So on the red spot, WA must be equal to WB. This gives us a second equation that we can use together with this equation to calculate the amount of load carried over in a certain direction. So we got WA equals WB. We are using the known formulas from the elastic theory of elements or the known formulas of applied mechanics. Then we know for simply supported beam or slab, it will be this. This is the deflection. Uncracked section must be equal to that. You can simplify it and you got this relationship. But we know that the total load is the sum of the two loads QA plus QB. And now you can start with substituting QB in this formula. When you do so, you have the load carried over in the direction of A, which is proportional to the dimensions of the slab in plan view. The same you can do in the other direction, of course, it is just purely symmetrically. In general, the load carried over in one direction A is a function, only a function of the geometry of the slab. So in our case, for simply supported on all sides, it is this simple formula. You can now consider a cyclic permutation. It means you change A in B and B in A, and you have this formula, which is exactly the same as stated before. For a square slab, for instance, simply supported on all sides, we know then that A is equal to B. We apply the formula QA over Q. We apply this formula and you see that it's a half, which is logic. It's a square. It's pure symmetrically in the two axes, so it should be the half. Half of the load is carried over to one side and half of the load is carried over to the other side. Same happens here to the other side. Then the bending moment, it's Q span squared divided by 8, or expressed in total load Q, it's Q8A squared over 16, and the same to the other direction because it is a square. So the maximum bending moment for a square slab, simply supported on all sides, is the total load in kilonewton per square meter and the total load multiplied by the span squared divided by 16. We use the method of equal deflection by counting on the well-known formulas for deflection and bending moments from applied mechanics. And just to give you, to help or to support your memory, you can use, for instance, the list of formulas given by the American Forest of Paper Associations in America. And then you have your system and the different bending moments, shear force, and so on. We are here interested in the maximum deflection in midspan, or we are interested in the deflection in the midspan of the slab. So this is this formula 5 divided by 384 and so on. When it's clamped, you also have similar formulas. Now, you must be careful when one side is, for instance, simply supported and the other one is fixed. This is not a symmetrical situation, so the deflection that we are looking for is not the maximum deflection, but deflection in midspan. So you have to take this formula and take x equal to L over 2. So it's always the equal deflection at the center of the slab. Now we can generalize this for all types of slabs, for slabs 1 to 6. And you see that for all slabs 1 to 6, you have different situations, which is simply supported on both sides. Maximum deflection is given by this formula. You can have another situation where it is fixed and clamped. Then the deflection in the middle of the span is this formula. And when it's fixed on both sides, then the maximum of the deflection in the middle of the span is this formula. You see now that all those terms are equal except the first figure here, and I call this omega. So this is omega 5, this is omega 2, and this is omega 1. All 6 slabs are a combination of those 3 different cases. So our formula becomes now that the proportion of load carried over in the A direction is equal to 1 divided by 1 plus omega A over omega B times A over B to the power 4. So this is a very powerful formula that we can use. By cyclic permutation, you of course have the proportion of load that's carried over in the direction of B. When you got the proportion of load that is carried over, then you can calculate the bending moment. The bending moment is based on the well-known formulas from the applied mechanics. In general, it is the load times the span squared divided by a coefficient. And this coefficient differs in the 3 cases that we have seen. Simply supported, of course, for the sagging bending moment, alpha A is 8. For the hogging bending moment, which is 0, means that alpha A is in fact infinity. Clamped and simply supported, we know then that alpha A is 128 divided by 9, and for the hogging bending moment, it's of course 8. And when it's clamped on both sides, sagging bending moment alpha A is 24, and the hogging bending moment is 12. Now we have all the tools to calculate very quickly and very easy all the bending moments and the load transfer. We give an example. For instance, we will estimate and make an estimate of the transfer of loads to the supports. We have an isolated slab. For instance, the slab can be continuous in the X direction. So we take this as clamped or fixed, clamped or fixed. And this is simply supported and simply supported. It's a type 3 slab. This is 5 meters, this is 4 meters, and it is loaded with 10 kilonewton per square meter. Now the question is, what portion of the load is transferred to this side and what portion of the load is transferred to the other side? Let's first take the load transfer to the side in the direction of A. Then we apply our formula that we just have developed, and QA is then the total load, 10 divided by 1 plus omega A, because this is clamped, so omega A is 1. The other side, omega B, this is simply supported, so it's 5. The size of A is 5 and the size of B is 4. So very quickly you see that the load transfer in the direction of A is 6.72 kilonewton per square meter. We will do the same formula. We apply the same formula in the other direction. So it means it's a total load divided by 1 plus, this is now omega B, which is 5. Omega A is 1. And then the length of B is 4 and of A is 5. So we arrive at 3.28. We can do the check. We add them up both and we see that we arrive at 10, which is what we expect, the total load transfer to this side now is QB, which is 3.28 times 4 the total span length divided of course by 2, because the other half is on this side. So now we have 6.56 kilonewton per meter. And on the other side we can do the same. So you see now, nevertheless, that the span is in the direction of A. It's much bigger. It's bigger than the one in the direction of A. Because of the fixed ends, it takes more load than the other side, and significantly more. And finally, you can plot the formula QA over Q, which is a function of A over B, and you can make a plot on the x-axis. It is 0.5 up till 2.5 for the proportion A over B. And on the y-axis, you take you plot the proportion of load carried over in one direction, A, divided by the total load. And now you have 6 types of slabs. You do it 6 times, but of course, when the slab is completely symmetrically, for instance, type 1 and type 6, type 1 is simply supported on all sides and type 6 is fixed on all sides. So it means that of course the carried over load is exactly the same for those 2 slabs. The same for type 4, because it's symmetrically completely the same in the A direction or the B direction is the same. So this is only one curve. And the other type of slabs have their own curve. What is very peculiar is that for a value A over B of 0.5 or less, the carried over load is almost the same as the total load. So this means that this is a one-way slab. So you can define one-way slabs when one side of the slab is larger than 2 times the other side, or when it's smaller than the half. It's just it's the same thing. So this is where the definition of one-way slab is coming from. Another thing is that for each type of slab, there is a specific proportion A over B, where the carried over load is identical. So QA is equal to QB, or the QA over Q is a half. And you will see that, for instance, for those slabs completely symmetrically, yeah, it's obvious that then A is equal to B, then QA is equal to QB. But you will see, for instance, for type 3, when 2 opposite sides are clamped and the other 2 opposite sides are fixed, are simply supported, sorry, then you will see that the carried over load is equal when A over B is 1.5.